Okay, everybody, so for this screencast, we're going to do something called the output error method. So basically, what the output error method does is you assume that we have, for example, a parachute in free fall. If you write the equations of motion for a parachute in free fall, you have here z double dot is negative g plus 1 over 2m rho z dot squared scd, and where this is the gravity term and this is the aerodynamic term. It's a 1D motion, very, very simple. Now what we assume is that we have the data z of t as a function of time that's been given in table format. And what I've done is I've actually taken the data here and placed it into a text file. So I can go into here and I can say clear CLC, close all, and I can do a DLM read of data.txt, and then time is data all comma 1, and z is data all comma 2. Essentially z is the second column. So I'm going to throw in a figure, I'm going to throw in a plot time comma z, and then I'm going to throw a hold on for later. I'm going to plot this, and here I have z as a function of time. So this is the data that I've imported. So the question then is how do I find my drag coefficient? What if I know the initial condition, I know the initial velocity, I know gravity, I know the free air density, I know the cross-sectional area of the parachute, I know the mass, but I don't know CD. So to do the output error method, what you do is you start with an initial guess, CD. So I'm going to put this over here, and I'm going to put this over here. So I'm going to say CD guess equals, and I'm just going to guess what it is. I'm going to say it's 0.8. And then I'm going to use this initial guess to obtain z tilde. So I'm going to say I'm going to say I'm just going to say z tilde is equal to, and then how do I get z tilde? Well, I have the equations of motion here. I'm just going to use Euler's method to compute z tilde. So then I'm going to say my Euler, and then I think I just need to give it the time vector. So then let's go to back to here, and let's make a new method, function z tilde equals, what was the function name? It was my Euler, and then the time vector. So I'm going to say that delta t is time of 2 minus time of 1, and then I just do my typical while loop. So I'm going to say t of 1 is 0. I'm going to say z tilde of 1 is, what was the initial condition? The initial condition was 100. Z tilde dot of 1 is, the initial condition there was 0. And then I just say while, and then I can actually just do, yeah, that's fine. T of 1 is time of 1. I can probably do that. And I can say while t is less than 10. And this is very, very inefficient coding, but it's okay. This is called my Euler. I had to save that, and it's not less than 10. It's less than time at end, whatever the end time is. Okay. I'm actually going to make this less efficient. I'm going to say t equals time. I'm going to make this more efficient. I'm going to say z tilde equals zeros of length of time, comma 1. I'm going to say z tilde dot is z tilde, and then I'm going to say z tilde of 1 is 100, z tilde dot of 1 is 0. I'm going to get rid of the while, or the while. I'm going to do for index equals 1 to length of time, and I like that better. That's more efficient coding. Okay, why doesn't it like this? Because it's not used. That's fine. So now I'm just going to go through Euler's method. So z tilde of index, and I guess I have to do minus 1. Index plus 1 equals z tilde, and I'm actually gonna name this n. It'll be easier if I name it n. Z tilde of n is n plus 1 is z tilde of n plus z tilde dot of n times delta t, and then z tilde dot of n plus 1 is z tilde dot of n plus z tilde double dot times delta t. Now what's z tilde double dot? Well, that's simple. It's just negative g plus 1 over 2 times m times rho times z tilde dot n squared times s times cd guess. And so that means we actually need to make cd guess an input to our function. So you're going to come over here, cd guess. Okay. Now we need to find all our parameters. G equals 9.81. Rho is 1.225. M, I think, was 10. S was 1. Okay, so let's run this, see if this works. Looks like we didn't, let's see, it didn't like delta t. I don't need that. Undefined function of variable delta. Oh, okay, I spelled it delta. It's delta t. And it looks like it worked. I didn't get any errors. So now let's do plot time, comma, z tilde, and let's plot it in red. And so here's my two graphs. Now, you notice here that in this case, CD guess was 0.8, and it flew slower, so it didn't fall as fast. So if you make it say 0.5, it looks like I'm right on the money, and 0.2, it looks like I fell too quickly. It looks like the actual answer might be CD5. So I can do like guess and check on this until I find it. But what if I have multiple parameters? Well, it's too hard to do multiple guesses. So instead what you do is you compute the total error between z and z tilde by doing z minus z tilde, the whole thing squared, adding everything together, and dividing by the number of points. So what I'm going to do there is I'm going to say, okay, my error is 1, I'm going to say n equals length of time, and I'm going to say my error is 1 over n times z minus z tilde dot hat squared. And then now I should have my error output. So currently, and that's and I need to do sum of all of that. So I get a number 43. So if I make it 0.5, I wonder if the error is 0.0017. So it's close, but not quite. So that's what, a Newton-Raphson technique can get rid of. So our initial error is 43. The goal then is to naturally perform an optimization technique to compute CD tilde such that the error drops to 0 or at least a minimum. So to minimize this problem, the Newton-Raphson technique is used such that E prime is, so you do CD of the current iteration minus E prime of CD tilde divided by E double prime CD tilde, and then that equals the next iteration. So basically all we need to do is to say, okay, while my error is greater than, say, 1e negative 3, you continue to iterate. So then you just say CD guess equals CD guess minus E prime of CD guess, and we're going to have to write this function later, and then E double prime of CD guess. Okay? So now we need to write the function E prime, right? So in order to do E prime, we need function out equals E prime of CD guess. And what we're going to do is we're going to do, so is that capital CD, capital CD guess. I'm going to save this as E prime. Oh, I saved it wrong. File, save as, .m. We want to use, I'm going to go ahead and use forward differencing. So basically what we want to do is we want to go over to output error method and copy this. And it looks like we're going to have to give the function z. And n can just be length of z. That's the same. So now we need to compute z tilde, right? So for forward differencing, we want out to be e plus, so basically the equation is e of x plus del x minus e of x all over del x. So I'm going to say del CD equals 0.1. I'm going to vary CD. I'm going to do 0.01. And then I need to compute my error 2, which I'm going to call this guy here. And I'm going to call this CD tilde 2. And then I'm going to compute my error 1, which is the same thing except z tilde 1. Now to get z tilde 2, I want to compute my Euler, and I have to give it time, comma, and I need to give it CD guess. So I'm going to give it CD guess plus del CD. And then for z tilde 1, I'm going to give it my Euler time, comma, CD guess. And then I'm going to say out is my error 2 minus my error 1 divided by del CD. Okay? So let's see. Time doesn't exist in here, so I need to give the function time. So e prime, I need to give the function time. And here I need to give the function time. Okay? So now we need to make e double prime. And we also need to compute my error in here. My error is this guy. So at the after every iteration, we also need to recompute the error. Otherwise, we won't keep going. So now we need to make e double prime. So now we make a new function, function out equals e double prime. I think, and I have to look, it's time CD guess z, time CD guess z. And it's going to be very, very similar to this. We're going to do forward differencing, except out does not equal this anymore. It equals something different. So in order to do that, I need to look this up on Sakai. Okay, so I have Sakai pulled up here. So I have f double prime xi is approximately f of xi plus 2 minus 2 f of xi plus 1 plus f of xi over delta x squared. So that means I need e of CD plus, or x plus del, 2 times del x minus 2 times e of x plus del x plus f, or e of x, all of that divided by del x squared. So when I have here CD C tilde 2, I need to do 2 times that. When I have C tilde 1, I need to add del CD. And then I also need a Z tilde 0, which is my Euler time CD guess by itself. Compute my error again and call that CD tilde 0. And then I can use the formula my error 2 minus 2 times my error 1 plus my error 0, and it looks like I named this improperly, my error 0. All of that divided by del x squared, or I guess del CD, sorry. And that should be it. So let's debug this and see if we don't run into an error. So if I run this, my solution should converge to the actual number. Now, it looks like I got a nan. Okay, so let's put this in debug mode. I'm going to step in. CD guess is this 0.8. Time is a big vector. My error 2 is 45. My error 1 is 43. Out is 224. So that's 45 minus 43 over 0.01. CD guess became negative. So it looks like because it came negative, what we need to do is add an alpha parameter in order to damp out our estimation. So remember, alpha can be anywhere between 0 and 1. So now I'm going to try to run this. And there we go. We have converged to the solution. If we look at CD guess, it went from, looks like if we maybe throw in a pause here, we can watch it, or we went from 0.8 to 0.7 to 0.65, and we slowly converged. We could also plot this inside it, and then we can actually watch the lines get closer and closer to the true solution. So really, the output error method is a way to integrate equations of motion, compute the error between your numerical solution and your actual data that you pulled from here, and then use a modified Newton-Raphson technique to minimize the problem. And in order to get your derivatives, you use numerical forward differencing for the first and second derivative. And as you know, the good thing about Newton-Raphson is you can actually expand it to multi-dimensions, so you can actually estimate more than just one parameter. So say you have a cube with, say, Cx, Cy, and Cz, you can use Newton-Raphson to estimate those coefficients. All right, good luck.